if the closed neighborhood of any vertex intersection every color class Vi is non-empty. So for every V in V. So in other words, if I take a color class, either it should contain a vertex V or it should contain at least one of its neighbors. Okay. So every color class should be a dominating set. So that is called as fall coloring, and the minimum K is called as fall chromatic number F. And then the second parameter is B coloring. So this is coloring of the vertices in such a way that every color class should have a vertex. Okay. That vertex should have a neighbor in all the other classes. So it is enough if you have one vertex which has a neighbor in all the other color classes, and the maximum I is B chromatic number denoted by chi B. And the third definition, I will be dealing it with a little bit in detail. So that is dom chromatic number. So you take DC to be the number of color classes that are dominating sets. Okay. So take any chromatic coloring. A graph can have many different chromatic colorings. So the number of color classes, suppose if it's in one chromatic coloring, you may have more number of dominating sets. In another, you may have lesser number of dominating sets. So you find out DC. That is the number of color classes which are dominating sets, and taking maximum over all possible chromatic colorings. That is DOM chromatic number. Okay. So you give a proper coloring for the vertices, collect all the color classes, find the number of color classes which are dominating sets, and maximum of that number. Maximum taken over all possible colorings, proper colorings. That is denoted by DOM chromatic number D chi. And then this chromatic transversal domination. You know, if you are given a set of lines, and a transversal means it is a line that should intersect all of them. So that is the motivation for defining this parameter. So a chromatic transversal domination set, it is a dominating set which intersects every color class of every chi coloring. So the minimum cardinality is the chromatic transversal domination number. So let me first start with this fifth parameter, that is dominator coloring. So motivated by a paper of Cocaine, Guerra, he defined this dominator coloring, and later Professor Armugam and his student Shahul Hamid, they have made many reasonable contributions to this parameter. Okay. So you take a vertex V, take a subset S of the vertex set. I say that this vertex V is a dominator of that set if V is adjacent to all the vertices in S. Okay. Or in other words, V dominates S. So you take a partition pi. Every element of this partition is a color class in our definition. So you have V1, V2, etc., Vk, any partition. So it is called as a dominator partition if every vertex should be a dominator of at least one Vi. So what you have is, for every vertex V, I should have at least one element of this partition, and that vertex should be adjacent to all the vertices in that partition. So that is called as a dominator partition. And the dominator partition number, pi d of G, that equals the minimum K for which your graph has a dominator partition. Okay. And if my pi is a proper coloring, then I have a dominator coloring. So the elements of my partition are color classes. So the dominator chromatic number denoted by chi d. So that is the minimum number of colors required for a dominator coloring. Now coming to the existence of this parameter, if you take every vertex as a color class. So suppose if my graph has n vertices, I take every Vi as a color class, and definitely every vertex dominates itself. So for every vertex, for every Vi, the corresponding singleton Vi will have that property, dominator property. And so this is a dominator partition. Okay. Not necessarily the minimum. So the upper bound for my parameter is n, and this shows the existence of chi d. Okay. So any graph will have this chi d, which is called as dominator chromatic number. So it is defined for every parameter. So if you look at this graph, you can see that it is a bipartite graph. And so you know that its proper coloring is this. Okay. So let me have a, okay. Can you see a whiteboard, sir?
Yes, madam.
Yes, madam. Yes.
Yeah. Oh, okay. So let me draw a graph, draw the same graph. Okay. So I have this. So this is adjacent to this. This one. This is adjacent to this. So you know it is a bipartite graph. So the chromatic number is 2. So let me give all these vertices color 1 and all these vertices color 2. And let me label them as A, B, C, D, E and F. Okay. So my two color classes are ABC is one color class, DEF is another color class. But you can see that if you look at the vertex 1, okay, the vertex A, B and C, A is adjacent to all the vertices with color 2. So A has the dominator property, but B does not have the dominator property. B is adjacent to only 2 vertices of the second color class, not to D. Okay. So B, C as well as D, they do not have the dominator property. So what I do now is, instead of having this 2, okay, instead of having this 2, suppose I give color 3. So I change 3. Now every vertex will have the dominator property. Already A, B, C, A have the dominator property. If you look at B, it is adjacent to all the vertices with the color class 2. Okay, so B has the dominator property. C has the dominator property. Coming to 3, 3 is adjacent to, okay, itself, because 3 is a single color class. So singleton 3 is the color class, so that will take care of the dominator property. So for this, chi D is 3. Okay. So this is how you find out chi D. So chromatic number for the graph is 2, whereas this chromatic number, that is dominator chromatic number, is 3. And coming to this graph, you can see that it has chromatic number 3 and it has a K3. Okay, this graph has a K3. So I need to color all the vertices of this K3 with each with one color. So I use 3 colors. And for every pendant, I can take an unused color. Okay, a color different from that of the support. So the chromatic number is 3. Whereas it can, that particular any chromatic coloring, of course, it has a chromatic coloring, this fixed. It is not a dominator coloring, because if I give color 1 for this, okay, and suppose if I give color 2, then this vertex will lose the dominator property, because it is adjacent to this vertex with color 2, but it is not adjacent to this vertex with color 2. So any color of used in this particular triangle cannot be used for the pendant, because if I use it, then that particular pendant vertex will lose the dominator property. So I need a 4th color. So that is for all the pendant vertices. Now every vertex will have the dominator property. So for this graph, chi D is 4. Okay. And then we shall compute the number for some standard graphs. If you look at by star, and if you have the condition m plus n greater than or equal to 4, you can see that for the by star, the chromatic number is 2. For the 2 vertices of degree greater than 1, you can have 2 different colors, and the corresponding pendant vertices can be colored with the other color. So chi is 2, whereas 2 colors will not be a dominator coloring. So you need a 3rd color. So for the 2 supports, you use 2 different colors, and for all the pendants, you use the corresponding color. So you have a chi D coloring with 3 vertices, and for k 1, n, I can manage with 2, and for kn, it is n. The chromatic number itself is n. So chi D of kn is n. and this is for the path which you have to compute. So for 2, 3, 4, 5 and 7, I compute it separately. And for n greater than or equal to 8, you have this number. Coming to the wheel, the center vertex, that has to be used a color, and actually that is a singleton color class because it is adjacent to all the other vertices. So the center vertex is one color class. Actually, that color class itself will take care of the dominator property, because if you take any vertex on the outer cycle that is adjacent to this vertex, so the dominator property will be taken care of that single vertex. So the remaining part is to color the vertices of a cycle. Okay, and you know that if the cycle is even, you need 2 colors, and if the cycle is odd, you need 3 colors. So that number plus 1 gives KD. So this is 2 plus 1 and this is 3 plus 1. And for the complete k-partite graph, if I have, so I have k partitions. All the vertices of one partition can be colored with the same color. So KD of that is found to be k. And then you can generalize star to be a...
Madam, will you please make a full screen?
Okay, okay. So if I take a multi-star, multi-star is a generalization of the star. You can view the star as K1, K1 sitting in the middle with pendants attached to that. So K2 of some 2 numbers, A1, A2 means I have a K2, and each vertex you can have any number of pendants. So it is a double star. Now coming to K3. So I have a K3, and at every vertex of K3, I can have any number of pendants. So in one vertex, I will have A1 pendant. In one vertex, I have A2 number of pendants, and so on. So you have number of unicyclic graphs. So it is a multi-star generalization of a star. Okay. So if you look at a multi-star Km formed by joining pendant vertices to every vertex of a complete graph, then for that, if you take chi of k, n of A1, A2, etc., actually it has to be n. Okay. So in order to color Kn itself, I need n colors. And for all the pendant vertices, I need 1 color. So the chromatic, it is actually KD also the same thing. So KD is also n plus 1. The chromatic coloring itself will be a dominator coloring. And this is for a cycle. Okay. And in the paper by Guerra et al., they have conjectured that KD of Qn, that is the hypercube, is 2 plus 2 power n minus 2. But later you will be, in this session itself, you will be proving that KD is less than or equal to gamma plus chi. Okay. So for Q7, KD of Q7 is less than or equal to gamma plus chi of that. So you know gamma of Q7 is 16. And hypercube is a bipartite graph. So chi is 2. So you have 18. And this value is much larger. So the conjecture is false. Okay. And of course, always every dominator coloring is a proper coloring. So it is always true that chi less than or equal to chi d for any graph. Okay. And both the strict inequality as well as equality, both of them are possible. For strict inequality, you can consider the bi-star. We saw that for the bi-star, chi is 2, whereas chi d is 3. So you have strict inequality there. And coming to k, 1, n, both of them are equal. Okay. And then if you take a graph G and a subgraph, you can see that in some cases, the subgraph will have lesser dominator chromatic number than the original graph. And in some cases, it may have larger. Okay. For both the things, I have given examples. If you take G as Kn and H is the subgraph, the complete bipartite graph A comma B, of course, where A and B are equal to n, I can observe that chi d of H is 2. Okay. Whereas for G, it is n. And then if you take G as Kn comma n and H as the path on 2n vertices, P2n, then chi d of H will be this. Definitely it is greater than or equal to 5, whereas chi d of the original graph, that is Kn comma n, that is 2. Okay. And this is a upper bound for chi d in terms of the independence number. That is the maximum number of vertices in an independent set. Okay. Idea is simple. I want to show that chi d is less than or equal to this. So I have to give a proper coloring. Okay, I have to give a coloring in which, of course, having this using this many colors. Okay, a proper coloring in which that particular coloring should be a dominator coloring. So what you do is you take an independent set I. Okay, I is an independent set, and being independent, I can use the same color for all the vertices in I. So I color all the vertices of I with one color. Okay, and consider G minus that I, and so you have n minus alpha of G vertices there. Every vertex there is taken as a single color class. So for every vertex, I use a distinct color. So the number of colors that I have used is n minus alpha plus 1. Okay. And now I can show that this coloring, it's a proper coloring, and this proper coloring is a dominator coloring. Okay. If you look at any vertex outside, that itself is a color class. So it will be that color class will take care of that dominator property. Coming to a vertex in I, the graph is connected. So definitely every vertex in I will have a neighbor outside, at least one neighbor outside, and every neighbor outside is a single color class. So every vertex in I also has the dominator property. So this is a very simple upper bound for chi d in terms of independence number. And the characterization is an open problem. Okay. And for the sharpness, I can go to B m comma n. You have alpha of B m comma n, that is the number, all the pendants, that is m plus n, which is p minus 2. Okay, so you can have that it is 3. Chi d, the upper bound is 3. And you know that chi d for bi star is 3. So you have equality here. And this is a characterization for these two upper bounds. That is, for any graph of order n greater than or equal to 2, chi d lies between 2 and n. Okay. And these two things are characterized. That is the lower bound as well as the upper bound. Chi d is 2 means if and only if my graph is the complete bipartite graph k a comma b, and chi d is n if and only if my graph is kn. Okay. Again, one part is obvious. If I take k a comma b, it is 2. Take chi d as 2. So I have two color classes. Okay. And it is a dominator coloring. I want to show that it is k a comma b. Suppose if the color classes are taken as v1 and v2, if either cardinality of v1 is 1 or cardinality of v2 is 1, okay, then the vertex in the color class v1 should be adjacent to all the vertices. Okay, it will be taken care of itself. Okay, and coming to the color class v2, that should be all the vertices there should be adjacent to this color class. Okay, so in that case, I will have k1 comma n minus 1. Suppose if both the color classes have at least 2 vertices. So cardinality of v1 is greater than or equal to 2, as well as cardinality of v2 is also greater than or equal to 2. Okay. Now, if you take a vertex small v1 in the color class v1, definitely it cannot be adjacent to the other vertices in that color class. So to maintain the dominator property, that vertex has to be adjacent to all the vertices of the second color class. So every vertex in v1 should be adjacent to every vertex in v2. So you have it to be a complete bipartite graph k a comma b. And coming to the characterization for chi d equal to n, I want to say that it is kn. So suppose if two vertices are non-adjacent, so in that case, suppose if x and y are non-adjacent, I can color x and y using the same color. So I will have one color class containing 2 vertices. So definitely chi d equal to n is contradicted. So no 2 vertices can be non-adjacent. So your graph should be kn. And this is a generalization of maybe this connected is removed. Okay. So if you take any graph of order n, then chi d equal to n if and only if instead of kn I have a ka union all the other components should be trivial graph. So what I want to prove is it can have only one non-trivial component. Other than that, every other component should be the trivial component. So what will happen if I have two non-trivial components, say G1 and G2? Pick up one vertex from G1, pick up another vertex from G2, color both of them with the same colors. That will be a dominator coloring. So you get a contradiction to chi d equal to n. Okay. So this is a generalization of the first theorem. And then another upper bound for chi d in terms of gamma. So take, of course, here you have both gamma as well as chi. This is a parameter which relates gamma and chi. So naturally this lower bound as well as upper bound, both of them are in terms of chi and gamma. So it is for a connected graph. You can see that every chi d coloring is also a chi coloring. So chi less than or equal to that. I can also show that gamma is less than or equal to chi d. So it is enough if I give a dominating set with cardinality chi d. Okay, so that gamma will be less than or equal to that. So take a dominator coloring partition. From every color class, pick up one vertex. Okay, so you have V1, V2, etc. V chi d. I claim that this is a dominating set. So take this set as S. Take any vertex V in V minus S. By the dominating coloring property, V will be adjacent to all the vertices of one color class, say capital Vi. And in this particular S, you have a representative from that Vi. Okay, say small Vi. So definitely that vertex will be taken care of small Vi. So this set with chi d elements, that is a dominating set. So you have gamma less than or equal to chi d. So the better lower bound is the maximum of these two. So maximum of chi of G comma gamma of G. That is the lower bound for chi d. And this is, of course, this is a very large upper bound. So you take any chromatic coloring chi. So take a chromatic coloring for the graph. From that graph, you pick up a dominating set. Recolor the vertices of the dominating set. So already you have used chi colors and you take only the vertices of the dominating set and recolor them, each with one color. So I have now chi plus gamma colors. Okay. And I can claim that this is a dominator coloring because if I take inside, every vertex is a color class. So all the vertices inside S will be taken care of. Okay. If you take a vertex outside, this is a dominating set. So every vertex outside is adjacent to at least one vertex inside. And the inside vertices are all singleton color classes. Okay, so the dominator property is maintained. So I have given you a dominator coloring using chi plus gamma colors. So chi d is less than or equal to that one. Okay. And sharpness for the lower bound is you can use complete bipartite graph. Okay. Because both chi as well as gamma, both of them are 2. And the upper bound holds for even cycles Cn. Okay, for n greater than or equal to 8. Okay. And then if you have a connected graph, this is one another property. If gamma is 1, okay, then I want to show that chi and chi d are equal. So gamma is 1. So my graph has a k 1 comma n minus 1 sitting inside, not necessarily induced. Okay, but I have a k 1 comma n minus 1. So I can color that one as by a single color. And since it is adjacent to all the other vertices, I cannot use that color to any of the other colors. So my chi of G will be same as chi of G minus V plus 1. Okay. So I have, and that single vertex alone is enough to take care of chi d. So the proper coloring, the chi coloring itself will be a dominator coloring. Dominator property will be taken care of that vertex with full degree. So you have chi equal to chi d. And if of course this is a realization theorem. If you take any pair 1 comma a with a greater than or equal to 1, I can find a graph with gamma equal to 1 and both chi g and chi d equal to a. What you do is you take a ka. For this a, you take a Ka and attach remaining pendant vertices to that particular, okay, you are taking a Ka and the remaining all other pendant vertices is attached to one vertex of Ka. So gamma is 1 because Ka, there is a complete graph on A vertices and in one vertex you have all the other pendants. So gamma is 1 and chi is A because you have attached pendants only at one vertex. So in order to color Ka, you need A colors. And the color that is not used for the support can be used to color the pendant. So chi as well as chi D, and that itself, this coloring itself will be a dominator coloring. So chi as well as chi D, both of them are equal to A. Of course, this is a typical construction. Okay, I don't go into that. So if you have any graph with delta equal to 1, then you can see that chi D is greater than gamma. So here again, it is enough if I give a dominating set with chi D colors. So I have delta equal to 1. So I have pendant vertices. So let me take a chi D coloring in such a way that all the pendants are put together in one color class, that is V1. And you can see that in any dominator coloring, every support has to sit alone because the dominator property is to be taken care of by pendant vertex. And you know that a pendant vertex should be adjacent to only to the support. So either you should have a pendant vertex as a single color class or you should have the support as a single color class. Okay. So my chi D coloring will contain all the support vertices as singletons. Okay. So you take this and you can prove that it is a dominating set. Okay. That is because if you take any vertex inside, if you take any Vi, okay, that Vi should be adjacent to at least all the elements of at least one color class. Okay. If it is one, if it is the color class V1, then either the vertex is a support or it is a leaf. So it is taken care of that. If it is a support, it is taken care of that singleton. Okay. If it is a leaf, it is inside the partition V1. So it is okay. It will be adjacent to that corresponding support. So that will be taken care of the dominator property. And so you can see that chi D is greater than gamma. Okay. This is in search of triangle-free graphs with arbitrarily large chromatic number. Because whenever you have a triangle, automatically you see that the chromatic number should be minimum 3. But even if there is no triangle at all, okay, you can have triangle-free graphs, but the chromatic number can be made as large as possible. And for that, you can have this Mysil-Skene graph. Okay. Of course, it is a typical construction where it is well known. In many labeling problems are done in this Mysil-Skene graph. Okay. So this is a small variation of this parameter done by Shahul and Rajeshwari in their PhD thesis. It is called as global dominator coloring. So you include in some way similar to global domination, you define this global dominator coloring. So a single vertex V is a dominator, means it is adjacent to every vertex of the set S. Okay. So similarly, you define a parameter called anti-dominator. So a vertex V is said to be an anti-dominator if V dominates none of the vertices of S. So it is not adjacent to any of the vertices of S. So that is called as an anti-dominator. So now, if I take a coloring V1 to Vk, okay, so a color class will be called as a DOM color class if a vertex is adjacent to, okay, or I have a vertex adjacent to all the vertices of Vi, and it is called as an anti-DOM color class if of a vertex V, if V is not adjacent to any of the Vi. Okay. So with this terminology, you can define a coloring to be a global dominator coloring if you add one more condition. The original condition of DOM coloring is dominator coloring is every vertex of G should be adjacent to all the vertices of one color class. And now an additional condition, it is not adjacent to every vertex of another color class. So I am going to search two color classes. One color class V should be adjacent to all the vertices of that color class, and another color class V is not adjacent to any vertex of the color class. Okay. So this, if this condition is the number of colors required for a coloring with this condition, that is called as global dominator chromatic number, and it is denoted by chi GD. So it is a small variation of this dominator coloring number called as chi GD. So if you look at this graph, you can see that chi is 2. Okay. And chi D, because this is a bi-star, so I cannot manage with 2 colors. So I need 3. So chi D is 3. But 3 coloring will not be a global dominator coloring, because your 3 coloring is this vertex will be given 1 color, this will be given the second color, and all the pendant vertices will be given the third color. So definitely it is not a global dominator coloring, because if you look at this pendant, it will be adjacent to this color class. Okay. But if you look at this, okay, it is okay, it is not adjacent to this particular vertex is okay. Coming to this one, okay, this particular vertex, it is adjacent to, this is a single color class, so it is adjacent to that color class. So dominator property is taken care of this vertex, and I need an anti-dom color class now. So I should have a color class, and this should not be adjacent to any vertex of that color class, but I don't have anyone. So this is the second color class, this is adjacent to that. Third color class, all the pendant vertices. Okay, so again, for 2 of them, it is adjacent. So even though it has dominator property, this 3 coloring does not have anti-dominator property. So I need 4 colors. Okay, so color 1, color 2, these 2 pendants color 3, and these 2 pendants color 4. Now you can check that every vertex will have a DOM color class as well as anti-DOM color class. Okay, so this number, this chi GD, that is 4. Okay. And this is a relation, of course, chi D is always less than or equal to chi GD, because you are adding an additional condition. And you can see that if G is a connected graph with chi D greater than or equal to delta plus 2, then these 2 things are equal. Okay. So you take any chi D coloring, you want to show that it is also a global dominator coloring. So a chi D coloring has chi D color classes. Take any vertex V. So V will be a member of one color class. So let me take it as V1. Okay. And capital delta is there. So definitely it can have only up to capital delta neighbors. So this particular vertex V, okay, it can have neighbors in delta minus, in okay, at most delta color classes, because the maximum degree is delta. So this vertex can have neighbors in at most delta color classes, but totally you have delta of G plus 2 color classes. So the vertex is in one color class. The neighbors can be in at the most delta color classes. So delta plus 1 is over, but I have at least one more left. So every V will not be adjacent to any vertex of that color class. Okay. So for every vertex, you have a DOM color class as well as an anti-DOM color class. And so this chi D itself is a global dominator coloring. Okay. And using this, you can immediately show that for the Peterson graph, you have chi GD is equal to 5. Because for the Peterson graph, you know delta is 3. Okay. And chi D is 5. So 5 greater than or equal to this. This condition equality holds here. So by this theorem, chi GD for Peterson graph is 5. Okay. So finding chi GD itself is a very big problem, because you have to check for every vertex, okay, whether it has a DOM color class as well as an anti-DOM color class. So if the graph is large, okay, it is not that easy. And of course, this is for chi GD is 2. Okay. So you have two color classes, global dominating. Okay. And suppose if one color class contains 2 vertices, 2 or more vertices, what I can say that is not a DOM color class. So that vertex has to be adjacent to all the other vertices of the second color class. So it does not have an anti-DOM color class. So a color class can contain only one vertex. So I have two color classes, each is a singleton. Okay. And suppose if those two are adjacent, then again it does not have an anti-DOM color class. So I have it to be non-adjacent. So my graph is K2 bar. Okay. Is my time over, sir?
3 minutes more, madam.
Okay. So let me just give a introduction. And of course, again, I already have given the definition. Okay. So this is the motivation. So Walliker, he proved that if a graph is K chromatic, any K coloring will give another K coloring containing a color class which is a dominating set. Okay. For example, if I take this particular thing, if I take this particular graph, okay, that is, okay. So I have a C4, okay, an edge, a triangle. Sorry for drawing like this, and then this one, okay. And you can see that I have a triangle. So definitely I need three colors. So color 1, color 2, color 2, color 3, color 2, color 1, color 3, color 1, color 3. So you have three color classes, and you can see that no color class is a dominating set. If you look at all the vertices with one color 1, it is not a dominating set. This vertex will not be taken care of. If you take all the vertices with color 2, that is not a dominating set. And all the vertices with color 3, again, that is not a dominating set. But Walliker proved that you can recolor this graph using, of course, the same three colors in such a way that it is a dominating set. Okay, that can be done. If you use one here, instead of using three here, suppose if I use one here, then the vertices with color 1 will be a dominating set. Okay, so that is the idea behind this. So this is the motivation for defining. This theorem is the motivation for giving this definition. So you take any K coloring V1, V2, etc. Vk. So you have to find out the number of color classes which are dominating. So then D chi is maximum of DC. So there may be K colorings without any dominating sets, but definitely you will have one in which some color classes are dominating sets. So this parameter will exist. So find out maximum of all such color classes. Okay, all such colorings. That is called as DOM color number, denoted by D chi. So here we have computed the value for, in many cases you can see that D chi equal to chi. Okay. And this is the obvious upper bound for D chi, 1 less than or equal to D chi less than or equal to chi. Okay. And then you have some realization theorems for which D chi, okay, if you have A and B, if you have such an inequality, okay, you can have a graph with D chi equal to A and chi equal to B. And if a graph is uniquely colorable, then both D chi and chi, both of them are equal, but the converse is not true. Okay. So one of my students, instead of taking maximum, he took minimum. Okay. So minimum of C, where the minimum is taken over all K colorings of G. So in some cases, you may have it to be 0. Okay. So this is called as the min DOM color number. So similarly, we could prove many results in this also. Okay. Of course, let me skip the values that I have found out. So you have so many characterizations to be done here with chi D equal to chi. Okay, chi D equal to gamma and chi GD. Okay, with chi DG also, you have open problems. Okay. So with MD chi also, I have open problems, and you can see that dominator chromatic number may increase arbitrarily when you remove a vertex. If I take the wheel, and suppose if I remove the middle vertex, that is the central vertex of the wheel, then chi D increases arbitrarily because you don't have one dominator coloring. When you looked at WN, you saw that the dominator property was taken care of that center vertex. So you need not worry about dominator property then. Okay. But now if I remove it, then I can have arbitrarily large dominator number. So the study of changing and unchanging dominator chromatic number, that is also an interesting problem. Okay. And these are of course the papers that I referred. And I have given my PDF to the organizers. So whoever interested, you can have a look at the PDF. So now,
Thank you, madam.
Thank you, ma'am.
Yeah. Very nice talk, starting from brief idea of domination and then moving up to dome. And I think if somebody has listened it very carefully, they will able to find out the problems also, because your last slide says what are the open problems.
Yeah,
so
yeah.
they can obviously start thinking about it. Any question from the audience?
Madam, I don't have any question, but compliments to Dr. Kala, because
Yes.
in line with your comments, I also agree with you. It was a wonderful lecture and given and delivered in nicest way. People will not find only the open problems, but also learn how to deliver a lecture.
So thank you, sir. Thank you for the compliment.
So that is also there, and so many open problems, and one can discuss the coloring as well as domination number, and such coloring and domination in the context of various coloring variants. So that is there is a wide scope of research work can be taken out from this invited talk. Thank you, ma'am, for giving a wonderful lecture.
Thank you very much, sir, for your compliments.
Thank you.
Kala, for a nice talk.
Thank you, ma'am. Thank you.
I just want to share some thought which came to my mind.
Yeah, ma'am.
Because due to some operations on the graph, the number does not change. For example, if I take two complete graphs and of the same order, and individually they have n chromatic, the number of words, so n chromatic number. If I join both of them with a common vertex, okay, that is I join on a common, then the chromatic number also remains the same.
Join means concatenating, ma'am. Concatenating. Yeah.
Joining means I do this one.
Okay.
And what I will be interested in your talk, I will be interested to find out, or from you other things, what can be said about your dominator plotting number with respect to operations where it does not change with respect to the graph. If, for example, if I take a cycle, its line graph will be a cycle.
Yeah. Okay.
If I take a path, its line graph will also be a path with less number of vertices and less length. And on the other hand, if I take see any vertex of degree greater than or equal to 3 is going to give us a complete graph. Further, if you take a bi-star, and then you get what I have told you, will be having two complete graphs with this vertex in common. So I will be interested to know, of course I will think about that one, how the global domination and other things, the dominator coloring behave with respect to some operations on the graph, or let me say derived graphs.
Okay.
Line graph.
Derived graphs. Okay. Yeah.
Total semi-graph, line cut graph. There's so many derived graphs are there.
Yeah.
So have you seen such a work? Have you thought about such type?
No, ma'am. No.
Okay. Thank you. Then I will try. Because I'm not in domination, but sometimes you don't know your mind where it will go and where it will work. Thank you for this one. I will ask the organizers to put on the.
Thank you, ma'am. Thank you.
Thank you very much, Kala.
Thank you, Mukti, madam.
Okay. Nita.
So, and now we thank Professor Kala for accepting invitation on behalf of NCETDM, and hope sometimes in future we will meet physically. If Dr. Chirag organize it in Patan, I attend you. So thank you very much.
Sure, ma'am. Sure. Thank you, ma'am. Thank you.
So next speaker we have as Dr. Chirag, a young, energetic faculty member of Department of Mathematics, Hemchandracharya, North Gujarat University. He has the experience of 17 years, and his expertise is graph theory, labeling, and now new research area, according to my knowledge, has been added to his credit, that is topological indices. He has in his credit 22 published papers, one book chapter, and one book. He will be discussing on combined degree sum of energy of a graph. Over to you, Dr. Chirag.
Thank you, madam. Thank you. Let me share my presentation first, madam.
Yes, sir. Yes, sir.
Is my presentation visible to?
Yes, sir. Yes, sir. Make it a full screen. Yes, go ahead, please.
Thank you very much, madam, for allowing me to give a presentation on some beautiful conjectures in graph theory and its present state. And at the end of the presentation, I will be discussing a new approach to handle the conjectures. I'll start with the very basic definition of what is conjecture. A conjecture is a conclusion or a proposition which is suspected to be true due to preliminary supporting evidence, but for which no proof or disproof has yet been found. This type of statements are known as conjectures, and it has been made by the renowned mathematicians most of the time. Let's come down to the definition of what do you mean by a beautiful conjecture. And according to Hardy, the mathematicians' patterns, like the painters or the poets, must be beautiful. The ideas, like the colors or the words, must fit together in a harmonious way. It is the first test, and there is no permanent place in this world for ugly mathematics. And that's what the thoughts of the Hardy, and that's, I think, must be fitted for the definition for the what we mean by a beautiful conjecture. And to evaluate any conjecture, Bondi has set down some criteria. The first criteria is simplicity. The conjecture should be short, easily understandable statement relating very basic concepts. While the second criteria which need to be set it down is elements of surprise. It must link together seemingly disparate concepts. The third criteria to evaluation of any conjecture is generality. It must be valid for wide variety of objects. This all criteria has been set it down by the Bondi. And we may add or something else also for this evaluation. Centrality, it must have a close ties with the number of existing theorems or conjectures. It must be at least 20 years old, that is the longevity criteria. And faculty criteria, While attempting to prove the conjectures, it must lead to some new concepts or new proofing techniques. That's the last criteria he has set it down. Before moving to any of the conjectures, let me give some basic definitions which I'm going to require to explain some of the concepts. The one is the diagraph. We all understand it has two sets. One first set is known as a vertex set, which is non-empty, and the other is an arc set, possibly empty. It doesn't matter. And every element of the arc set is assigned an ordered pair of vertices. And a dipath is a path in a diagraph it is a finite sequence having the alternating vertices and edges as a terms. And two connected graph is a graph from which we need to remove at least two vertices to make it a disconnected. And girth of a graph is the girth of an undirected graph is the length of the shortest cycle contained in the graph. And similarly, for directed graph, it is known as directed girth, and it is the minimum length of the directed cycle. And if the girth, if there is no, if the graph doesn't contain any cycle, then the girth would be defined to be infinite. Let me come down to the first conjecture, which I am interested also, is in the labeling technique. That is a good age labeling. Let me first tell you how it is how it is motivated from a practical problem. Madam, it has been it has a very close link with the networking problem. Nowadays, the internet, we are using the internet in two modes, like Wi-Fi and the cabled connection. But for the transferring data from one continent to other continents, they are using the fiber optical network. And it has one particular, what we can say, one particular property that wavelength division multiplication, multiplexing would be required to understand this thing. What is wavelength division multiplexing? It is a fiber optimal transmission technique that enables us to use the multiple light wavelengths, or what we can say colors, to send data over the same medium. On the same medium, if you wish to send multiple data, then the techniques which we are using is called wavelength division multiplexing. Two or more colors of lights can travel on one fiber only, or several signals can be transmitted in an optical waveguide at a different wavelengths or frequencies on the optical spectrum. The problem we are having here is called the routing and wavelength assignment problem, which is shortly known as a RWA problem in wavelength division multiplexing networks. It consists of finding routes and their associate wavelengths to satisfy a set of traffic requirement while minimizing the number of wavelengths used. And because of this contains this, it has been already proved that the RWA problem are NP hard. And that's why this problem has been divided into two parts. It is divided into two different problems. The first problem is to find out for each request, find the roots, and that is the first problem. And when we have done with the first problem, then the second problem comes. The root founded in the first problems are taken as an input and associate wavelengths to them in such a way that two roots using the same fiber do not have the same wavelength. Now, when we focused on the second problem, it can be reformulated as we can convert it into a graph theoretical problem as a considering a digraph and set of die paths, each of which corresponds to the roots of the request, and find the minimum number of wavelengths W need to associate, need to assign on different different die paths sharing an edge. And if we generate a conflict graph taking one vertex per die path and two vertices are adjacent in conflict graph in the corresponding die path shares an edge, then this conflict, this undirected conflict graph, if we are considering that graph only, and then the problem 2 reduces to find the chromatic number of the conflict graph. Vermonts and others studied this RWA problem for directed acyclic graphs for having the unique die path property. What do you mean by unique die path property? That for any two vertices, there exists only one die path between them. That is called the unique die path property. And while studying this thing in their research report, they have defined this good age labeling. And let me define now what good age labeling is. An age labeling for graph G is a function phi from age set of the graph to the real number line. And when we have done that, we now focusing on a path is a path is called increasing path or is increasing if the sequence of its age label is non-decreasing. An age labeling of graph G is called good, or a graph is called a good graph for any two distinct vertices U and V. There exists at most one increasing UV path. And if this condition need not be satisfied by a graph, then it is called a bad graph. Equivalently, if we consider this, for finite undirected simple graph G, good age labeling of G is an assignment of distinct numbers to the ages in such a way that every cycle has at least two local maximums. A graph G is good age labeling critical if it has no good age labeling, but every proper subgraph has a good age labeling. Now, let us discuss some known results related to good age labeling. The graph K3 and K22 have known to be no good age labeling. They are not good graphs. It has been already proved in that paper. And this good age labeling is having hereditary property. That is, every subgraph of graph G having good age labeling also have a good age labeling. And this is an interesting one. There exists a family of graph with a good age labeling and a chromatic number as large as B. The chromatic number, the graph with having a n chromatic number and it is a good age labeling. Yes, we can have it. So these are the known results. And now let's come down to the conjecture. What the conjecture is, what is the statement of the conjecture? It says that for every C less than 4, there is only a finite number of good age labeling critical graphs with average degree less than C. It has been proposed by Araujo and others in 2009. It is not that long, it is not that old, but because of the simplicity and generality, I have taken up this concept. And once they have proposed that, currently, up till now, it has been proved that boards and others have proved that they have found out an example of a minimal graph without good age labeling with the average degree 3. This is the first step, and that has been proved in 2011. And Araujo and others proved that the forest C3 free outer planar graphs, planar graphs of at least 6 are good graphs. They have published this paper in Discrete Applied Mathematics in 2012. And Mehrabian have shown that there exists graphs with arbitrarily large growth that do not have a good age labeling. And Mehrabians and others have proved that n vertex graph having a good age labeling must has at most half n log n ages, and that this bound is sharp for infinitely many. So we cannot breach this bound. The graph must have at most have this many ages only. And this is all about the good age labeling. No other work has been done in that part. And the conjecture is still open. Now, moving further, let me come down to very well-known two conjectures. The first one is known as a path decomposition conjecture, and the second one is known as a cycle decomposition conjecture. Both are motivated from one result of those. Let me first give the definition of what do you mean by decomposition. A decomposition of graph G is a family script f of edges, each disjoint subgraph H, such that when we take a union of all the edge set of the subgraphs in the family, it covers all the edges of the graph G. If all the subgraphs are path graphs, then the decomposition is known as a path decomposition. And similarly, when we replace subgraphs by cycle, then it is known as a cycle decomposition. Every graph can be decomposed into paths, while for cycle decomposition, a graph G must be an Eulerian. And it is if and only Eulerian graphs can be decomposed into cycles. Let me give you one example for path decomposition. I have considered this graph. This is the first path I have considered, first subgraph. The second subgraph is shown using the blue color, the third one, and the fourth. So this graph can be decomposed into 4 subgraphs, each disjoint subgraph. Similarly, one more example I have taken, and in this is the first one, second, and third. It can become decomposed by using 3 subgraphs. I have given one example of cycle decomposition too. This I have taken is a first cycle. This is second one, and this is third one. Of course, this is an Eulerian graph. The degree of each vertex is even in this, and this is a connected one. Even the connectedness is not required for both the conjectures, but I have considered the example for connectedness. Now let's come down to the path decomposition conjecture. The statement says that every connected simple graph on n vertices can be decomposed into at most n+1 parts. I'm sure everyone is student. And this conjecture has been posted by Galai in 1968. On all 6 parameters, it has simplicity 3 stars, generality 3 stars, centrality, longevity, and all this. The bound given in this conjecture is a sharp one, as for complete graph, the bound has been attained. Now let me show you. I have taken the complete graph K5. So n is equal to 5, and n+1 by 2, that is 6 by 2. Yes, n+1 by 2, that is 6 by 2. And that means we need to have 3 parts. We require 3 parts to decompose this K5. Let me show you. This is the first one. This is the second path I have considered. And still there are 2 edges left, so that I have covered using the third. And it is not possible to decompose the K5 less than n+1 by 2, that is 3 parts. Similarly, one more example I have taken for K6. And for K6, we would be requiring 6+1 by 2, that is 7 by 2, 3.5. And lower bound of it is 3 parts. We can decompose the K6 using 3 parts. This is the first one. And this is the second one, second path. This is the third. So the bound is sharp. Now, many researchers have, since it is posted way back, many researchers have started working on it. And in fact, this particular conjectures has motivated from the first result. A graph G on n vertices by lowest. N vertices can be decomposed into floor part of n by 2 parts plus n cycle. And the same paper, they have verified the conjectures for graphs having at most 1 vertex with even degree. That has been already by them. While Faber has extended Loaz's result by proving that the conjecture holds for graphs in which each cycle contains at least 1 vertex with a odd degree. The bound has been extended. The condition has been relaxed a little. While Bonamy and Parrott have confirmed that conjecture is true for all graphs with maximum degree at most 5. To understand the next result, we need to have a definition of a block. A block in a graph G is a maximal 2 connected subgraph of G. And a path number, the path number of graph G is denoted by PNG, is the minimum number of paths required to decompose G. And the friend has proved that the connected graph G having n vertices can be decomposed in at most floor part of n by 2 vertices if it has at most 1 even vertex. And if the subgraph of G induces by even vertex is a forest, then also the result holds. And if each block of the subgraph of G induces by even vertex is triangle free and has maximum degree at most 3, then also the result holds. Many other researchers have also contributed to settle down this conjecture and published many papers. Currently, Professor Bolter and the team is working on these conjectures. They have published several papers on it. Still, the conjecture remains open though it looks very simple to prove, but no proof has been found yet. A similar conjecture has been defined for cycle decomposition. And the conjecture states that every simple Eulerian graph on n vertices can be decomposed into at most n minus 1 by 2 cycles. There we have required n plus 1 by 2 paths, and here we have at most n minus 1 by 2 cycles. This conjecture has been proposed by Hedges in 1968. And again, on all parameters, it is very simple to understand, and it has very many applications, and new proofing technique has been developed, but it survives is still. And again, the bound given in the conjecture is sharp for complete graphs, as in this example I am demonstrating it. To decompose the K5 in using cycles, 5 means n has equal to 5, that is n minus 1 by 2 equal to 2. We require 2 cycles. This is the first one, and this is the second one, to settle down the to decompose complete graph K5 using cycles. Similarly, to decompose K7, we required at least three cycles. No less than 3 cycles can be useful to. It is not possible to decompose K7 using less than 3 cycles. Though the cycle decomposition conjecture and path decomposition conjectures looks very similar, a very little progress has been made for cycle decomposition. People have found it very difficult one to move further, and have made some progress in the cycle decomposition. There are only a handful of papers available on this. Say 4 that proves that every simple even planar graph on n vertices satisfies the conjecture. Simple even planar graph, and he presented this result in 1990. While Granville and Moissaid, it shows that the conjecture is satisfied for all Eulerian graph with maximum degree at most 4. And Penn and Zhu have verified the conjectures for projective graphs and K6 minus and age minor free graphs. While Hendricks and others have verified the conjecture for all Eulerian graphs with up to 12 vertices. They have taken the algorithm and proved it using the computer that up to all Eulerian graph up to 12 vertices satisfies the conjecture. And the other team of Hendricks have verified the conjecture for all small graphs. Professor Bolter and others have verified the conjecture for graph with 3 at most 3, while Professor Fuchs and his team has improved the result for path width at most 6. And this is where the progress comes to an end. There are no further progress has been made in this cycle decomposition conjecture, and still this path decomposition conjecture and cycle decomposition conjectures are open. And the last result has been given by the group led by Professor Gerio. Then they would discuss the conjecture for dense graph. Now, let's come down to a novel approach to attack the conjecture. And that is known as an AI approach. AI stands for the artificial intelligence. As my favorite author, Dan Brown, suggested in his fiction Origin, that the next evaluation happens, and then it should be a mix of artificial intelligence and human intellect. And the new version would be, new evaluation would be based on that only. How we can approach any conjecture using AI? Let me come down to that part very quickly. In AI, there is one concept called reinforcement learning. And reinforcement learning, what we are doing in reinforcement learning is we set certain rules, and we feed them to the program, and then program learns by itself by the by playing certain criteria or certain scenarios by itself, and come down with the beautiful results. Let me give you some models based on that. That is predictive model, classification model, and generative models are based on the reinforcement learning. Predictive model, there are sites like shadi.com or 99acres.com are working on. They have got very large data and very many properties to be need to take care of. Likewise, in shadi.com, if someone creates a profile and it comes down with the suggestions that this many matches are most suitable for you, they'll decide based on the location, caste, the education background, the professional background, the hobbies, the dietary, the family backgrounds, and everything they'll taken care of, and they'll decide it based on that. The model has been developed in that way. But in classification models, if I feed the program with 1,000 different photographs of, let's say, a lion and a goat, and make the program understand that thing, that this is how the lion would look like, and this is how the goat would look like. Program will try to understand how the features of lion and goats are separated. And then when I give them the problem of having next photograph, 1001 photograph, and if I ask the program to verify it whether the picture is of a lion or a goat, most probably the program will predict it correctly. Similar type of approach can be used for facial recognition or facial expressions and many other type of things. While in generative model, if I feed them with the information, computer will generate a new model or a new object out of the information he got. Likewise, how I would be looked like after 20 years. So there are many applications available nowadays which generates how you would look like after 20 years or 10 years time. They are using this type of reinforcement learning models. Actually, in this reinforcement learning, computers are reaching to the superhuman level in the play in games like Go, purely through self-play. The first breakthrough comes in October 2015 when the program called AlphaGo Zero beats the Go World Champion, human Go World Champion. The game called Go is considered to be the most complex game, having very many certain rules. And for this reinforcement learning algorithms, there are no programs available which purely focusing on or have the learning ability which can beat the human immature human player. But this AlphaGo has proven us wrong, and this is to be recorded as a big success for machine learning and as well as an AI approach. Now, how can we convert this type of reinforcement learning into our mathematical modeling? Instead of feeding the rules for the chess or Go game, we can feed them with the certain rules in graph theory. Likewise, we can use the reinforcement learning algorithms could be used to find explicit counter examples to conjectures in combinatorics and graph theory. How we can do it? Let me give you one process.
Sir, 5 minutes more.
Yep, I'll wrap it down in 5 minutes. Yes. The program starts the learning process with zero prior knowledge about the problem itself. And we just feed the constraints and receives the feedback from the scoring function at how well the program has done the construction. And we make the program repeat this process many times. And from this, the program will learn how to get a better score in this. The scoring function could be anything. If this scoring, if the score is larger than the score of the conjectures, the best constructions, then the program has succeeded in finding a counterexample to the conjecture. That's what the process is. And an advantage of using reinforcement learning algorithm is that we can use it for the same exact program to try and attack all the mathematical conjectures, which might have a finite counterexamples by changing only the functions that calculate the scores of a given construction. This approach has been developed by the Professor Wagner from the Tel Aviv University, and interested learners can read the papers he has published. I have given the paper and the footnote in 2021. And he implemented it for many conjectures and found counterexamples on this. In fact, most of the time the program comes up with improved counterexamples for the conjectures which are already settled down. So I think that's it. I suppose I conclude my talk with the statement of Descartes that with me everything turns into mathematics. This is also true for me. So I must have believed that for most of us this is true. So thank you very much. Thank you. If there are any questions?
Thank you, Dr. Chirag. Starting with a good graph and good age labeling, you reach to the most fascinating words of this decade, that is artificial intelligence. So more and more people will like to go with artificial intelligence and game theory. Now, an open question from the audience. Hello, any question from the audience? Mukti madam, any suggestion? So it seems there is no question till now. So it seems that your talk is now getting trained by neural network using artificial intelligence.
Thank you. Thank you.
Madam is having some problem. It seems she is muted. Yes, Professor Vaidya. Professor Vaidya.
Actually, I think
Now it is
All
okay.
of them are muted, it seems.
So some
Mukti
people-
madam, you need to mute.
I don't
Unmute.
have any questions, but because there are
No question, suggestion,
there are
madam,
a lot of
suggestion.
questions for the new generations. The good coverage, as you have told, this is needed because the young people who are attending this conference, they must have some problems. But little bit surprise to me from the participants. We people are already grown up, no? Age-wise. I don't say knowledge-wise. They are not asking any question. They are not asking any queries. That is missing. Participants must be hearing. So at least if there are, I don't know how many participants are attending, but there was a good 46 presentations and all.
91. 91.
Everyone is attending, but the thoughts are not coming to their minds. My question is, they should ask some questions, because such conferences are conducted only for the benefits of younger generations, new research comers. So my question, this one, and I congrats Chirag for his this covering more area of things which are open, where they can put their, I will not say put their hands, put their minds to settle those problems. Thank you very much.
Thank you very much, madam. Thank you.
वो आप
Thank you, madam.
से लोग वो कर देते हैं यहाँ. So when I click, I don't get unmute. What does not do this one? Okay.
Yeah, I agree with Mukti ma'am, and we can't ask or give any comment because temporarily we were muted. But anyway, I will like to add in the presentation and the information given by Dr. Chirag that is the Ringel-Korsak's conjecture. It is again regarding the cyclic decomposition and well celebrated conjecture. Or also it is popular as termed as the graceful tree conjecture. So in tune with Mukti ma'am's comment, I will like to suggest all the researchers, because there were so many presentations on labeling. So the researchers, those who are working in the field of labeling, for them this cyclic decomposition of the complete graph as well as path decompositions are very much a useful concept. So please read, and the mind which doubted are the mind that survived, as told by Sister Nivedita. So please ask questions. Sometimes we feel that, and people will feel that they are very trivial or foolish question, but it will help us a lot to acquire the information. With these comments, that's all fine from me.
Thank you, Vaid sir and Mukti madam.
Thank you.
So this session is over, and for the next session, I'm passing it on to the organizers of HNGU in association with Atmiya University. Thank you once again.
Thank you, madam.
Thank you, Nita ma'am, for such a nice handover and for sharing this wonderful session. So now I'll invite Professor H.S. Ramane sir to chair the next session. Dr. H.S. Ramane sir is a professor and chairman of the Department of Mathematics, Karnataka University. He also has served as a coordinator for UGC SAP programs and a coordinator for PAR program in the department. He has 25 years of teaching experience. He has collaborative research work with people from India and abroad. He's published 152 research papers in national and international journals. written 3 book chapters, participated in more than 100 conferences, and presented 25 papers and delivered 59 invited special talks and conferences. He has visited Indonesia, China, Taiwan for presentation of research papers and to deliver some invited talks. And so I hand over the session to you, Ramane sir. Yeah.
Thank you, ma'am. Audible, ma'am?
Yeah, you're audible.
Okay. Thanks for inviting me to chair this session. 10th invited talk for this session. We have Dr. Pranjali. He is assistant professor at the Department of Mathematics at University of Rajasthan. He has also worked at Basri University, Rajasthan. He completed her MSc from the Chaudhary Charan Singh University, Meerut, and PhD from University of Delhi. Her area of research is algebra and graph theory, embedding of graphs, combination in graphs, and side graphs. Today she is going to talk on Hamming distance labeling and its applications. Welcome, Dr. Panjali, and request you to please proceed with your lecture.
Good afternoon, one and all. First of all, thank you. Thank you very much, sir. I'm delighted and honored by your introduction. First of all, I would like to thank to Professor A.V. Kadia, Professor S.K. Vedya, Professor Neeta Shah, and Dr. Chirag, who has invited me to speak with a group of enlightened colleagues across the country. I'm thankful that I'm here as a part of this 3 days national conference on emerging trends in discrete mathematics. I pay my regards to Professor Mukti Acharya, late Dr. B.D. Acharya. I'm here just because of them and their effort. They have trained me like this, so I pay my regards to both my supervisor. As we all know that this is going to be last invited talk, so my effort is that this session should be end with some brain tonic, and I will try that none of you feel bored. So I'm going to start. Slides are visible?
Yeah, visible.
Yes, madam. Yes, madam.
Oh, okay. So we will be talking on Hamming distance K. Yes. Hamming distance labeling and its applications. So what will be our aim here? That we will be talking on Hamming distances and then its application. And then we will go move to Hamming graph by labeling technique. And then finally, we will discuss that what are the outcomes of the new concept on Hamming distance K labeling. So, first of all, since from last 2 years, we are facing this pandemic, and each one of us have been trained that we are using the digitalized mode. And in fact, today we also are meeting on virtual platform.
Sorry to disturb you, madam. Can you please make it the full screen?
Sir, I actually want to use this pen and okay, I'll just see. On that, I will not be able to use this pen.
Oh, okay, sorry.
So that's what I did like this.
Sure, no problem.
Anyway, if anyone is facing problem, then kindly let me know.
No, that thing is okay, perfect.
Okay, sir. So then we are using the virtual platform at each stage from last 2 years. Even the transactions have been become digitalized. We are receiving the OTP, and this OTP is very secret code. So if you are going to share it with someone, then it may harm. So this is the most prominent field, and the subject of graph theory is coding. So code, and this coding came after Richard Hamming, and he did work in coding. And in fact, this scheme came after his name. It is the association scheme where the elements are the vectors of length d over some alphabets of size q. In fact, a huge literature is available on Hamming graph and Hamming scheme. Now, just come to this code. What is a code actually? Any message in form of code. If I want to send this X, Y, Z, then this message is hidden in form of code, and if anyone will read it, then it's a meaningless jumble for him. However, it's a simple message coded in a specified way. There can be number associated with this message, or it is due to shifting of the alphabets. There can be a many specified way. And there are different ways to code this message. And in fact, there are associated approaches to decode them. So cryptography is basically a discipline where we are dealing with communication secrecy. In fact, code have been used since long by businessmen, government, and military for obvious reasons. In fact, if you want to send a message to your friend or partner and you don't want that it should be understood by someone else, then you will send it in some coding way. So there will be some coding, and who want to encrypt this message, he will decode. So even before the advent of computer, there was several ways to send the message by method of signal. Now, what will be the approach? So throughout work, since we want to use the binary digit 0, 1, so we will be using the respective field F2, the field with 2 elements, so 0 and 1. Now, and z to the power d is nothing but the z2 Cartesian product d times. And for each element of this set is either 0 or 1. So itself is a d tuple, and each xi is either 0 or 1. So now just let us have a, however, we all are familiar with standard basis, since coding is nothing but the blend of linear algebra as well as graph. So we can't forget the linear algebra. So standard basis are denoted by EI. So where E1 is nothing, the first tuple is 1 and rest all are 0. It itself can be n or d tuple, whatever is the requirement. So E0 is nothing but all the tuples are 0. Now, so here in this lecture, our focus will be on Hamming distance labeling. But what was the motivation behind the concept? See, already there exists literature on Hamming graph, and it is very much useful in coding theory. So what is our approach? That we have introduced Hamming distance k labeling, and with respect to this labeling, what we have shown that every graph admits Hamming distance 2 labeling, but not Hamming distance 1 labeling. However, we have characterized some graphs which admit the Hamming distance 1 labeling. In fact, this methodology is a blending of graphs as well as the linear algebra techniques. So let us know what is a Hamming graph first. So you have a set S. You have a set S and D be any positive integer, then Hamming graph HDQ has vertex set S to the power D, means suppose S is 1, 2 and D is also 2, then there will be tuples like 1, 1, 1, 2, 2, 1, 2, 2. So there will be 2 tuples over this set S. So all the elements are set of ordered tuples from A of S and 2 vertices. Since for a graph we require only 2 things, vertices and edges. So vertex set will coming from this S to the power D and 2 vertices are adjacent if they differ precisely in one coordinate. It means if like there is a trouble in using pen. A second. So if they differ, for example, this is 1, 0, this is 0, 1, then at the first place, it differs because it's 1, it is 0. So they differ at first places. And in fact, if we look at the second tuple, it is also different. So they are different at 2 places. But if I talk about the 1, 0 and 1, 1, then this place is similar, but this place is different. So they are differ precisely in one coordinate. So for Hamming graph, the pair will be adjacent if they differ precisely in one coordinate. So now look an example. Suppose my S is equals to 1, 2, and D I'm taking 1. Then what happens? Because I am not required any tuples, there is a 1 tuple because D has been setted as 1. So they are adjacent since they differ at exactly at 1 places. Now if I change my S, I will not change S, I will change the D, then there will be 2 to the power 2, there will be 4 vertices. So take the 4 vertices and how they will come? This is 1, 1, 1, 2, 2, 2, and 2, 1. So now these are the vertices of Hamming graph. Now, how 2 vertices will be adjacent? If they differ precisely at one coordinate. So look at here, they different at second places. So second tuple is different. Now similarly, this 2, 2, 1 and 2, 2, they also differ at one place. Similarly here, they are different at one place. Similarly here. So in this way, our Hamming graph have been constructed. These pair will not be adjacent since this is 2, this is 1. First place is different and as well as the second place is also different. So they differ at 2 coordinates. So they are not adjacent. So this is Hamming 22H22 graph. So now, so some beautiful examples of Hamming graph. If you will take D is equals to 1 and take S is any set with n elements, then H1Q is nothing but the complete graph. And on the other hand, if you set Q is equals to 1, then it's a single vertex because you have taken the elements from only the set which has cardinality 1. So it will be K1 only. Similarly, if we change D is equals to 2, then the Hamming 2Q in general is Q cross Q grid. In fact, it is also known as the lattice graph of order Q. These are the example. Now, what is our approach? We have Hamming graph. There are certain graphs which cannot be seen as Hamming graph. Now, our approach is that the graph which is not Hamming graph, can we embed this graph, arbitrary graph, of course, which is not Hamming graph, into a Hamming graph by some labeling technique. It means I am going to start with any G and I want to embed into Hamming graph so that with the help of function f. This is my objective. So now there are some useful definition because we had to relate it with Hamming distance. So let us know about what is the weight of a vector. So since the elements are coming from z to the power n, it is taken intentionally because the code which we want to send has to be converted into binary. So 0, 1 is required. That's what it has been taken, the elements of z to the power n. Now weight of a vector is what? Take the distance of this vector from the 0 vector. So in this way, we will receive the weight of vector. Or we can say that since the elements are 0 or 1 only, so number of ones in that string is known as the weight of that vector. So if I will take this vector, then number of ones is only 1. So weight of this vector 1, 0, 0 is nothing but 1. So here I have taken the example. Take x is equals to 0, 1, 1, 0, 1. And y is this. These are 5 tuples. So weight of this vector, since there are 3 ones, so weight is 3. And here there are 2 ones, so weight is 2. Now, this is the fact which is trivially can be seen that 2 vectors of different length can have the same weight. It is easy that the weight of this vector is also 1. And if I will take 0, 0, 0, 0, 1, weight of this vector is also same. So 2 vectors of different length, because in this way, this vector is taking from the elements of this 1, 0, 0 is the element of z to the power 3. However, this is the element of z to the power 5. So 2 vectors can have the same weight. Now, in order to see the Hamming distance, if you have 2 strings, x and y, and x is nothing, x1, x2, x3, and xn, because we have taken the elements of z to the power n, then how we define the sum? We define the sum of the corresponding entries or corresponding tuples of x and y. So x1, y1, x2, y2, and xn, yn. This is, so we will add these corresponding entries. And since the entries are the elements of Z2, so if both are equal, then the sum is going to be 0. For example, this is 1, this is also 1, then sum is going to be 2. But entries are coming from Z2, so it is going to be 0 under mod 2. If both are 0, then still the sum is 0. So if both are same, then this tuple is going to be, after adding, this tuple is going to be 0, otherwise 1. Now come to the concept of Hamming distance. The Hamming distance between 2 strings, so x and y are a string of length n, then Hamming distance between x and y is the number of i's where xi is not equals to yi. So what we want to find, that if x is equals to 1, 0, 0 and y is equals to 0, 1, 0, then Hamming distance between these 2 strings is given by the number of positions at which x and y are not same or x and y differ. Both are the same thing. So this is the place where they are different. So 1, then another, it is different. So 2, but it is same. So the Hamming distance between these 2 vectors, x and y, is 2. Okay. So, or it can be calculated that you sum these 2 vectors and then calculate the weight of x plus y, then it is same as the Hamming distance between x and y. So you can take a vector or a string and then sum it up by previous method that you have to sum the corresponding tuples and then calculate the weight of that. So in this way, we will be able to calculate the Hamming distance. Slide is visible to all of you? There is no trouble?
It's visible now. Visible.
Okay, fine. Because this is a one way, so I need to confirm that whether it's I'm connected or not.
Yeah.
Okay, sir. Thank you. So take an example that if take x is equals to 1, 1, 0, 0, y is equals to 1, 0, 1, 1, then x plus y is obtained 0, 1, 1, 1. Then if you look at the Hamming distance from here, that this place is same. So no, this place is different. So 1 is from here. Similarly, from second tuple, from second, third, fourth, second, third, and fourth places are different. So Hamming distance is 3. Because we have to look at how many places the entries differ. That if it is 0, then another has to be 1. And if we calculate the weight of this vector, then it is again 3. So Hamming distance can be calculated from the string that it is nothing but the weight of x plus y. Now, there are several applications of this Hamming distance. First of all, in coding, where codes are obtained from graph. In computer memory, where modem and embedded processors are involved. In telecommunication, for error detection and correction, even in nano satellites, and we have used in labeling. So let us have a glimpse of application in coding. What is a code? As I told earlier, that code is nothing but a message, but it has been modules in a specified way. For example, if you want to send it to you want to send RSY, you want to send this message, and it might be possible that you have converted it into 234. So, but if anyone will read, then he will just think that this is some numbers. But so code is what, according to now, we have to turn into mathematics. So code in our sense is a linear subspace of vector space. Of course, we are talking about binary. It's a vector subspace of z to the power n. Okay. So we know that this is a vector space over the field F2, where F2 is a finite field with 2 elements. So we take any subspace. Subspace means this, if you are taking 2 vectors, x and y, from this C, then alpha and alpha beta be the scalar from Z2, then alpha x plus beta y has to be in C only. This is the necessary and sufficient condition for the subspace. So code is nothing but it's a subspace of this vector space. I'm talking about binary. Now, what is the role of this n? This n is called the length of the code. And that since it's a vector subspace, so of course we can talk on finite dimensional vector space is there. So the dimension of this C is called the rank, and the elements, because vector subspace can have many elements, so the any element is called code word. So code is nothing but according to us is a subspace. According to us means I'm not specified to me as a mathematician. So now what is the minimal distance of a linear code? It is the minimum distance between distinct code words. For example, if C consists of small c1, c2, c3, there are 3 code words that can be of any length. Then minimum distance from C1 to C, we will calculate the distance from C1 to C2, C2 to C3 and C1 to C3, then operate the minimum over that. Then it will be the minimal distance of that code. So I just would like to explain this by an example. For example, consider a code. It has 4 code words. Each is of length 4. Of course, we are taking from the elements of, just facing some trouble. Z to the power 4, and each is of length 4, and there are 4 code words. It means, what I would like to say, that this subspace consists of 4 vectors, because vector space we are talking about. So these are 4 elements. So what they can be, since this is a subspace, they can be linearly dependent. I should not say, because 0 vector will be there, so it cannot be a linearly independent set. So now we will calculate the rank. So rank means dimension of C. So how many vectors are linearly independent? Because it will generate the Z to 4. So now we would like to see that how many of them are linearly independent. So if we look at here, 0 vector is there, so it cannot be included in the dimension. And for example, this vector is there, then these 2 vectors will generate this. Or I would say that C1, C2, C3, C4 are there, then the C3 can be expressed as the linear combination of C2 can be expressed as the linear combination of C3 and C4. So the rank will be 2. Now the minimal distance from this vector to this vector, look at the distance. This is 4. From here to here, the distance is 2. From here to here again, it is 4. And from here to here, it is 2. So minimum is 2, 4, 2, 4. The minimum will be coming from, it is 2. Okay. So now, what we have seen that if you how a code look like according to linear algebra. Now I want to move to the concept which I have been chosen for this lecture. So earlier what we were having, now I just don't want to go into the depth of this coding, but earlier what we have, that we have a graph and the code will be nkd over some array q. This is the q represent the field fq. This n is the length, k is the dimension, d is the minimum distance. All 3 have been discussed in just the previous slide. So nkd represent a code. Suppose we have a graph, then we can form an incidence matrix and then calculate the rank, and the rows of that incidence matrix forms a basis. Then this k will represent that how many rows are linearly independent, that will be defined by k, and d is the minimum distance from any 2 vectors, or I would say code. So graph can be associated with respect to a nkd code. Now, what is our aim? That we want to start from the code, and with the help of Hamming distance k labeling, I would be, if I am able to label the vertices, or I should say that my graph admit the Hamming distance k labeling, then this code can be sent with the help of that graph. So it means I want to correspond a code with the help of graph using the concept of Hamming distance k labeling. So what is a Hamming distance k labeling? Start from a graph, because we want to label the vertices, and V be the vertex set, and E denotes the edge set, and let HD denote the Hamming distance. Then inject a function from the vertex set to Z to the power n is called Hamming distance K labeling. If for each UV belonging into H, the Hamming distance of the correspond after the labeling, it should be K. So K being a positive integer, it means if you will give me K is equals to 1, then if I'm able to label my graph in such a way that if there is an adjacency, then after labeling, the Hamming distance of that pair has to be 1. Means the pair are adjacent. So if I'm going to label this by some vector x and this some vector y, then this xy must be at Hamming distance 1. If I'm talking about the k is equal to 1, but it's a generalized concept, so you can talk about the Hamming distance 2 labeling, Hamming distance 3 labeling, and so on. So let us look an example of Hamming distance 1 labeling. So it means whenever there is an adjacency, I should label the elements, or I should label that vertex with a vector in such a way that this Hamming distance is 1. Now, what about the non-adjacency? Non-adjacent pair may have Hamming distance 1. So because I'm not putting any condition on the non-adjacent pair. So take the elements from Z2 into Z2 into Z2, Z to the power 4. Of course, that is the necessary condition that if you have a graph with n vertex, then your n should be greater than Z to the power k. This n is either greater or equals to Z to the power k means 2 to the power. I just write. Because if the elements will be less, then I cannot put an injective function. So now we have taken the elements from Z to the power 4. So this pair, look at here, these are at Hamming distance 1 because there is a difference on the first tuple only. Similarly, if you look at here, there is a difference at second tuple only, and so on. So in that way, we can label the vertex. So non-adjacent pair can have the distance 1 or it is not necessary. So, but whenever there is adjacency, the Hamming distance has to be 1 only. So this was the example of Hamming distance 1 labeling of hypercube Q3. It has 8 vertices and I have taken a set with 16 elements. Now, another example of complete graph K4. We have, there are 4 vertices, all are mutually adjacent. Now I am going to use Z to the power 3. So this 1, 1, 1, and this is 0, 1, 1. So we can see that first and third tuple are different. So Hamming distance is 2. Here also Hamming distance. Here the second and third tuple are different. Similarly, all are at Hamming distance 2. So I think now everyone must have a question that does every graph admits Hamming distance K labeling for some K or for all K? So it might be possible that suppose I have a graph G, then it can admit the Hamming distance 1 labeling but not 2 labeling, or every graph admit Hamming distance 1 labeling. So this kind of question is natural to come at this stage. But what I did in the previous 2 examples, I just want to your attention on the previous 2 examples that if I will define the Hamming graph that HD, there is a concept of Hamming graph HQD that the pairs are adjacent whenever they have a Hamming distance 1. Okay. So in a Hamming graph, which exists in the literature, that the pair will be adjacent whenever there is a difference of precisely 1 coordinate. It means the graph which were not in the category of this, suppose this is the collection of Hamming graph. I'm sorry, just I will take 1 second to change the pen because it is not working properly. Okay. So HQD was our Hamming graph. Then if this is denote the collection of all Hamming graph, then there are some graph which do not belongs in the set. Then what I am going to convey, if I am able to label this graph, means I can, if I'm able to label the vertex of this graph, then it can be embedded into a Hamming graph. So it means the problem has been converted into an embedding problem. That if a graph is Hamming graph, then it is well and good. If it is not a Hamming graph, then we can label, or does there exist a function so that this graph can be embedded into a Hamming graph. Earlier it was not Hamming graph. So, but we have also generalized this concept. If I will define H1 QD, H2 QD, means the original Hamming graph, I will say that it is one, H1 QD. Then I am going to define the generalized concept that the pairs will be adjacent when the Hamming distance is K, or K can be given. So it is H2 QD is denotes that Hamming graph in which all the vertices are adjacent, where the Hamming distance is 2. So then in that way, if my graph admits the Hamming distance 2 labeling, then I would say that it can also be embedded into that Hamming graph. So if I would just say that this concept has been generalized to HKQD, and those who were not the graphs which were not earlier the Hamming graph for any K, then whether they can be embedded or not. This is now the problem has been converted into this. So towards digging this problem, we found that the answer is negative for all K, but it is affirmative for some K. If I just talk about that K is equals to 2, then my answer is affirmative, and I can embed any graph into my Hamming graph, H2QD. And I will be using this simple remark. Consider the set of standard bases of Q tuples. Then any two elements in S differ with exactly 2 coordinates, or I would say that they are at Hamming distance 2. Just look at here. This pair is different. This pair is also different. So Hamming distance is 2. Consider any set of standard bases of any tuples. So then they are at Hamming distance 2, or I should say they differ at 2 places. So with the help of that remark, we have proved that every finite graph admits the Hamming distance 2 labeling. It means if a graph is H2QD or not, but I can label and I can embed my arbitrary graph into this graph with the help of using the standard basis. Now then there is a problem which we have not tackled. Problem can be seen as an optimal case, that what will be the size of that Hamming graph, or you are using the S, how big you are using the S, can you reduce the size of S? So that problem is still open, that you can also reduce the size. Since every graph admits a labeling, so there will be a bound on HQD. So then we can think about how to reduce the size of S. Now there is a question of Hamming distance 1 labeling. Does every graph admits the Hamming distance 1 labeling? No. from the elements of Z to K, there does not exist any pair that we can label the complete graph where the pairs are at Hamming distance 1. So this is this problem again can be tackled, that characterize the graph which admits Hamming distance 1 labeling. So this is a question which can be seen, but we have partially solved this problem, that take a cycle of length n where n is even, then Cn admits the Hamming distance 1 labeling. Means cycle of all the cycle of even length admits the Hamming distance 1 labeling. Even we had also thought of course solved about the star graph, that is star graph.
Another 3 minutes.
Oh, 3 minutes. Yes, sir. I'm going to conclusion. Slides are okay. So just I would like to give some necessary condition that if take a finite graph and if it has an odd cycle, then it does not admit the Hamming distance 1 labeling. So then come to Kn, and these are the cases which have been tackled for graphs. But this is the one of the beautiful result. I would just take 1 second on it, that if a graph admits Hamming distance 1 labeling, then it also admits the Hamming distance K labeling for all K. It means if I am able to embed my graph into H1QD, then I can embed into higher class also. So that is one of the good results. So if we are able to prove that the cycle graph admits the Hamming distance 1 labeling, then it also admits the Hamming distance 2 labeling, 3 labeling, and so on. In fact, every finite graph, because we have shown that every finite graph admits Hamming distance 2 labeling. So by using that, we have also proved that every graph admits the Hamming distance K labeling for all even positive integers. So the problem came to on bipartite graph, because we have also given a necessary condition that if graph consists of odd cycle, then it cannot admit the Hamming distance 1 labeling. So characterize bipartite graph which admits the Hamming distance 1 labeling. This is again. So this problem has been converted into this. So the problem is we have to see only for bipartite graph. The following graph already has been proved that these graph admits the Hamming distance 1 labeling. So what is my emphasizes here, that if you have a code from the elements of Z to the power K, then I would like to send this code with the help of labeling. Suppose I am able to I am able to label the vertices of this graph from this C, because C can have many code words, or so suppose C has 4 code words, then I can send that code with the help of a graph which has 4 vertices, and which NKD we want to send. This K denotes the Hamming distance D. So if I would like to say that this is Hamming distance D is equal to 2, then I would like to mention that my graph should admit the Hamming distance 2 labeling. I'm not bothered about the Hamming, the non-adjacent pair. They can have at distance 4, but whenever there is an adjacency, the distance should be 2 only. So this was my contribution, and this coding problem is I'm already tackling that for some graph it already have been tackled, but I want to generalize it, so work is going on. This was all from my side. So if you have any questions, I would be happy to take if I can answer.
Pranjali?
Yes, sir.
Yeah, Dr. Pranjali, thank you for a nice and informative lecture. I have a small curious question. That is there any necessary condition for the existence of Hamming distance labeling?
We have not for Hamming distance one labeling we have a necessary condition, but for 2 and for NEK we do not have any necessary, because for 2 we can directly use the bases, elements of the bases.
Okay. And is there any forbidden characterization for a graph to admit Hamming distance scale labeling or distance one labeling?
No, sir, we have not seen yet the forbidden structure. So that can be seen.
Yeah, that can be treated as an open problem.
Yes, sir. Yes, sir.
Okay, that's good.
Thank you, sir.
Vaidya sir, any other question? Yes, I have some doubt. For length of the labeling, whether there is a restriction?
For, sir?
Length of a labeling. But
no, sir, that's what I told that then if every graph admits the Hamming distance to labeling, then we can reduce the size. Then optimality can be seen. That is again another paper can be worked on that. So because this work is just initiative, I have only written 2 papers on that. I am still working from coding. That's what I discussed on the last. That code can be sent with the help of graph. Earlier we have a graph, then we can find its code. There are so many paper codes from graph, but now I am going to write that how my codes can be converted into a graph. So the graph will be looking, so anyone who want to decode, he should know about the Hamming distance and labeling, and then he can decode.
Hello.
Yes, ma'am.
I have one thought.
Yes, ma'am.
What happens if you are able to embed?
Yes, ma'am.
Does not have a Hamming distance labeling to a Hamming distance labeling, then I think a forbidden subgraph characterization will not be possible. This is my thought. I have to verify.
Ma'am,
if you can embed any graph in other graph with that property, then I think that forbids us to have a forbidden subgraph characterization.
But ma'am, for Hamming distance one labeling, it is not possible. So as Professor S.K. Vaidya sir told that for Hamming distance one, we can find the forbidden structure. For k is equals to 1.
But once see forbidden structure for Hamming distance, K1, K2, all these have. But what are the forbidden structures? That you have to find out.
Yes. Yes, ma'am.
Okay, even you try with the cycle of length 3 admits this. So you take its corona with so many, you see whether it can be extended or not. But then your length of the vector will increase, no?
Increase, yes, ma'am. In fact,
so once it increases, you cannot emphasize that one. No, that's okay. We will think about that one. Okay.
Okay, ma'am. Okay.
Question that can be. I think that can be tackled.
Yes,
I have to try. Okay, Pranjali, thank you.
Thank you, ma'am. So
मैं तुमको अनथैंक यू नहीं कह सकती. थैंक यू ही होता है, ठीक है? Okay.
Okay, ma'am.
should say you. Thank you.
Thank you, Pranjali.
Thank you, sir. Thank you.
Giving the lecture on the
Yes, ma'am. Yes, ma'am. Please.
So I'm thankful to all the organizers, Ramne sir, Neeta ma'am, Vaidya sir, Acharya ma'am, and all academicians present here. So I'm very younger to all. So it's my contribution, and I'm on the journey. So I will follow the paths which already has been created by all the academicians. So I'm trying that, and I will try. This is my, with this word, I would like to thank you, and I want your blessings.
Good.
Thank you, ma'am.
Blessings are always there.
Yes, ma'am.
Okay, thank you. I thank all the participants for attending this party talk of the thank the organizers for giving me the opportunity to chair this session. Thank you, and hand over this.
Yes, Aditi, please.
Okay, so thank you, Ramani sir, for chairing the session so well. So now I will just grab a quick bite and meet back at 2 for the paper presentation session.
Before that, we have a group photo.
Yes, before that we'll have a group photo. I always forget. Just turn on your camera so that we can have a group photo. Okay.
Okay, bye.
Okay, bye.
See you.
See you at 2 p.m.
Surely.
Okay.
Yeah.
Surely.
Okay, once again, thank you very much.
Thank you, madam, for accepting our invitation.
Okay, thank you, sir. Thank you very much. I hope I have not bored to all the participants.
No, it was very interesting one.
Okay, thank you, sir.